Hi, I'm Lu Gan from the California Institute of Technology. In this presentation, I'll introduce our work on RGB-X object detection via scene-specific fusion modules. This is a joint work with the Ford Motor Company. Detecting objects such as vehicles, pedestrians, and traffic lights is vital for autonomous vehicles on the road. In recent years, with the availability of large-scale annotated datasets, vision-based object detection models achieved impressive results. However, as RGB cameras are highly dependent on lighting and visibility, vision-based object detection remains challenging in adverse weather conditions. Modern autonomous vehicles are usually equipped with multiple sensors with different pros and cons, including RGB camera, LiDAR, radar, and other supplemental sensors such as thermal camera. Fusing sensory measurements in different modalities provides an effective way to improve the system redundancy and the robustness of detection models. There are three types of sensor fusion mechanisms commonly used in the literature. The early fusion approach fuses raw sensor measurements in different modalities and processes the fused measurements together. Whereas in the middle level fusion, the fusion happens at the feature level. And lastly, the late fusion fuses the detection results from individual detection models, such as bounding boxes. Among the three mechanisms, deep sensor fusion on the feature level offers greater flexibility and generally shows better performance. However, there are also challenges in such fusion mechanism. Fusion at the feature level usually results in densely interconnected network architecture. Therefore, it requires large-scale co-registered multi-model training data that is hard to obtain, and extensive training time whenever a sensor component needs to be changed. In light of these challenges, in this work, we propose an efficient RGB-X fusion network that can leverage detection models pre-trained on abundant single-model datasets and reduce the requirement of co-registered multi-model data from training all parameters to only training lightweight fusion modules. This design offers the possibility of having multiple sets of fusion parameters for different scene conditions to bring scene adaptability. As a result, our model achieves superior performance over existing object detection methods on RGB thermal and RGB gated datasets, as well as comparable results with 75% less co-registered multi-model training data. For implementation, we use efficient data architecture with an efficient net backbone and a bi-FPN architecture pre-trained on single-model training data. During training, we keep the pre-trained parameters frozen and train several scene-specific fusion modules using co-registered images from different scene categories. For instance, from daytime, nighttime, overcast, and fog. We also use the pre-trained detector head to further reduce the number of training parameters. Our fusion module consists of several convolutional block attention modules, CBAM, to fuse multimodal features at various bi-FPN stages. Specifically, we first concatenate thermal and RGB features output from the respective bi-FPN. The concatenated feature maps go through a channel attention module and a spatial attention module. Finally, we use the 2D convolutional layer to revert the feature size to the original single model feature size. In addition, we also train a scene classifier on RGB features considering the high variance of RGB images under different scene categories. During inference, the scene classifier outputs the probabilities of the current scene categories given the input image. And we use the classification result as an indicator to select the corresponding scene-specific fusion module for multi-model feature fusion. This online fusion module selection allows the model to choose the optimal set of parameters for the current scene. resulting in a scene adaptive detection model with only small overhead. Now, we show some quantitative and qualitative results of our method compared with the state-of-the-art RGB-X fusion models for object detection on 3 multimodal datasets. First, we achieved the best RGB thermal object detection performance on FLIR-aligned dataset for all object categories. Here, the scene-agnostic C-band model refers to our model with only one set of C-band fusion modules trained on images from all scene categories. The large margin of our scene-agnostic model over the existing approaches shows the advantage of our method in leveraging pre-trained single model detectors. And our scene adaptive model further improved the performance over the scene agnostic model, clearly showing its adaptable ability for various scenes. Our fusion models also had superior performance on RGB-gated detections on the scene through fog multimodal dataset. Here are some visualized detection results for 6 different scene categories shown along with the ground truth bounding boxes, ranging from clear day to snow night. We found that our scene adaptive model generally works better than the scene agnostic model on harsh weather conditions like dense fog and snow, but perform similarly on clear day images. Here are more qualitative results on the M-qubit FD dataset for RGB thermal detections with zoom-in visualizations. We further visualized the learned channel attention of different scene-specific fusion modules by plotting the normalized attention weights for all feature channels in the trained C-band parameters. The pattern of an increasing reliance on thermal features over the RGB features from day to challenging scenes supports our idea of having different fusion modules for different scene conditions. Lastly, we conducted an experiment on the effect of training dataset size on the detection performance. In this experiment, we trained our fusion module using 100%, 50%, 25%, and 1% of the original datasets. As a result, we found that competitive results can still be achieved using only 25% of the original training data, showing our proposed model has reduced the reliance on co-registered multi-model training data. To conclude our work, we presented an RGB-X object detection framework that fuses pre-trained single-modal networks using lightweight fusion modules. Our approach reduces the dependence on hard-to-obtain co-registered RGB-X datasets, reduces fusion training time when sensors or pre-trained networks are swapped out, and provides improved adaptability via scene-specific fusion modules. Please refer to our paper and GitHub repository for more details. Lastly, we would like to acknowledge the Ford Motor Company for funding our work. Thank you.